Great energy and a great turnout for our first What Physicists Do talk of the semester. I have to say I am, yes, if people want to woo and clap. I heard that, that's good. So I won't wax poetically about, my Astronomy 100 students will know and I will not wax poetically about how important this series is to the intellectual life of the Physics and Astronomy department, but we think also of Sonoma State University and to the broader community who shows up here every week, and we just very much appreciate it. But I will start in right away to introduce Dr. Jeffrey Bennett. I am just thrilled, as I will describe here in a moment. A little background, he has his Bachelor of Arts in Biophysics from UC San Diego, and he followed that up with a PhD at in astrophysics at the University of Colorado, Boulder. But many of us in the astronomy community know him through his authorship of several award-winning textbooks and novels, including, I think, the book that's the general topic of the lecture today, which is, his book is A Global Warming Primer, and of course his talk, A Global Warming Demystified. For this work and for his communication of science, he won the very prestigious American Institute of Physics Science Communication Award, just to really the pinnacle of reaching out from the community of scientists to the broader public. My little personal thing about it is that in terms of textbooks, both his Astronomy 100, his introductory textbook, but this text, which is this thin little read but gets into such deep science in such a clear way, this is our textbook for our Frontiers in Astronomy course, and we use it in a sense, this is a little older text, and we use it as a before and after. He poses problems for the next millennium in astronomy, several which have been solved by really intrepid researchers, and we get to talk about the before and after of that science, and some questions that are certainly still under very active investigation today. So I want us to give Dr. Jeffrey Bennett a warm welcome. I'm going to ask him to sign my book. Thank you.
Thank you very much. Thanks for coming out this afternoon. It's a beautiful day out there. Has nothing to do with global warming, but I appreciate you being inside while it's so pretty out there. So yeah, what I try to do in my career is I focus on science communication, and I've done a lot of speaking over the years, but a couple years ago, I decided to do something a little different. In 2015, some of you will remember, it was the 100th anniversary of Einstein's publication of general relativity. And I wrote a book on relativity, and I got this email that went, I think, to all physicists in the world that said, if you can do something about public awareness of relativity during the 2015 100th anniversary celebration, please do. And I thought, well, I could go give talks about relativity. So I offered up to go give talks, and I ended up in 25 cities talking to more than 10,000 people in total about relativity. And then it was really fun. And then 2015 ended. It wasn't the 100th anniversary anymore. And okay, well, what do I do now? So I thought, well, what makes relativity such a great topic in terms of the public? Why was the public so enthused about hearing about relativity? And I think it kind of boiled down to two basic things. Number one, pretty much everybody's heard of relativity. And number two, but pretty much very few people have any idea what it actually is and why they've heard about it. So I thought, well, what else could I talk about that everybody's heard of, but very few people really understand much about? So this came to mind. So I decided I would go out and talk about global warming. Now, unlike the case with relativity, where I'd already written a book and went out and talked about it, I had not written a book on global warming, although I've written about it in my astronomy textbooks and lots of other places. And I decided I was going to do this talk answering your questions about the science, the consequences, and the solutions. And, you know, it's a 1-hour talk, and I've quickly found that in 1 hour I couldn't answer all your questions. And so I decided I had to write a book to answer the rest of the questions I didn't have time to get to. So I have a book called A Global Warming Primer. It would be wonderful if you bought it, but you don't have to because it's posted for free online at globalwarmingprimer.com. So this topic is really interesting because as you know, there's this debate that goes on in the media about global warming. And yet it's really a very simple topic, but you never hear that part talked about. Instead, what you hear is what you might think of as a debate over the details. And to put it in terms of common phraseology, I would say that what you hear in the debate is missing the forest for the trees. People are always debating these little details, this model, that measurement, and so on, but no one ever tells you what the big picture of this topic is. And so that's what I want to talk to you about today. 3 basic simple goals. Number 1, to try to explain the basic science to you. Number 2, to help you understand the debate that you hear in the media a bit. And maybe most important, although probably the shortest part of the talk, to show you that this problem is actually one that we can solve, and it's one that, despite what you may hear in the media, is not a political problem and does not require political disagreement to come to a solution to it. And just to give you a little bit of evidence that maybe I have a way of doing it that will show you that it's not political, there is a quote from his review of my book from Secretary Shultz, who was the secretary under President Reagan. So you can see this is not a liberal versus conservative issue, despite what you hear in the news. Now, I'm an astronomer by training. I write astronomy textbooks, astronomy books. How do I get into talking about global warming? It's because global warming is, in fact, an astronomical topic. And I think it's actually helpful if we approach it in an astronomical way. So what I want to do is start out with what I call a tale of 2 planets. And you can see right away that we're dealing astronomically, because we got 2 planets up there, and outside of astronomy you probably only deal with 1 planet, but we deal with lots of them in astronomy. Here, 2 in particular, Earth and Venus. And what you see here on the screen is those 2 planets shown to scale. And what you notice is they're the same size. In fact, you can't tell just by looking, but from other things that we know about these 2 planets, they're not only the same size, but they're basically made of the same thing. They have the same compositions. If you cut them open, they would look very, very similar inside. So for all practical purposes, we're dealing with 2 planets that are virtually identical. They're sometimes called twins for that reason. And yet there's one way in which they differ very greatly, and that is in their surface temperature. You can see we have a very nice, pleasant surface temperature here on Earth. Venus, not so much, hot enough to melt lead. What I want you to do when you hear about global warming is I want you to think about it like a scientist would think about it. In other words, to think scientifically, ask the questions that a scientist would ask, and try to come to answers based on evidence that will help you understand the science behind this. And so if you see this, and you're thinking like a scientist, the question that ought to come to mind is, if we have 2 worlds that are in almost every respect virtually twins of one another, why do they differ in this one major way? So to answer that question, you need to hypothesize. You need to think of what could it be that explains that one big difference between them. And most people, if you think a little bit about the solar system, you might guess that it's because Venus is closer to the sun. However, it turns out that's not the answer. And an easy way to tell that it's not the answer is to look at a scale model of the solar system. So this is one that we built on the National Mall in Washington, D.C. If you go out there, there's the Air and Space Museum. That is the sun at 1/10 billionth of actual size. It's about that big. Earth and Venus on that scale are smaller than the ballpoint in your pen, and they're located there and there. It's a little hard to tell in the perspective, but that's about 10 meters, 15 meters from the sun. And what you'll notice is, Venus is closer to the sun, obviously, but not by enough to account for that enormous difference in temperature. A good way to think about it is, imagine that this was a giant bonfire right here where the sun is. How much heat would you feel standing at Venus? How much heat would you feel standing at Earth? Yes, it's going to be warmer at Venus, but not by enough to account for that huge temperature difference. And in fact, if you study astronomy a little bit, or atmospheric science, you may notice something else in this picture, which is that Earth has a few clouds on it. Venus is completely covered in clouds. And you know that clouds reflect sunlight, and as a result, it turns out that even though Venus is closer to the sun, it actually gets less sunlight on the ground because of all the clouds reflecting so much light. So if all there was to it was distance from the sun and cloud cover, Venus would actually be colder than Earth. And yet it's not. It's way, way hotter. So that first hypothesis didn't work, closer to the sun. So now we have to hypothesize again. We could do that and spend a lot of time asking questions and guessing, but I'm just going to tell you the answer. The answer is the reason Venus is so hot is because of what we call the greenhouse effect. You've probably heard of the greenhouse effect before. It's really very simple. Much of the energy coming from the sun that heats the Earth is coming in the form of visible light that comes right down through the atmosphere, except for the part that's reflected, some by the surface and some by clouds. It gets absorbed by the ground. So the ground is absorbing this visible energy from the sun. It can't just hang on to that or it would heat up super quick. It has to return that energy back to space. It doesn't return it in the same form. You know that the ground is not returning the energy in the form of visible light because if it was, it would glow in the dark. It doesn't, therefore it must be returning it in some other form, and the form it's returning it in, represented by the red arrows here, is infrared light. Infrared light, it turns out there are certain molecules in the atmosphere that are very good at absorbing it. In particular, water vapor, carbon dioxide, and methane. Those are the three biggest absorbers of infrared light. So what happens is when infrared is coming back from the ground and it hits one of these greenhouse molecules, water vapor, carbon dioxide, or methane, it gets absorbed and then gets re-emitted. But when it's re-emitted, it's going to be in any random direction. And the result is that it bounces around among these molecules before it finally gets back out into space. And the more of these blue dots representing these greenhouse molecules you have, the more it's going to bounce around before it finally gets into space. And the net result of that is that you're keeping the energy down here close to the ground longer, and therefore you end up adding heat to the ground and the lower atmosphere. And the more of these blue dots you have, the more you're going to add. It's really completely analogous to a blanket. If you're outside on a cold night and you put a blanket around you, you get warmer. But think about it. The blanket doesn't give off any heat, right? All it's doing is slowing the escape of your own body heat. The more blankets you put around you, the more you slow that escape and the warmer you're able to be. So it's basically the same process. So that's the answer to why Venus is so much hotter. But remember, I told you I want you to think like a scientist. So if you're thinking like a scientist, you should be saying to yourself right now, Jeff, that's a nice story. Why should I believe you? So I need to give you evidence that this is really what's actually happening. What's the evidence? Well, the first form of evidence, how do we know that the greenhouse effect is real? We have two strong lines of evidence that together make it indisputable that this is, in fact, the answer. The first is that we can measure this effect, this trapping of heat by greenhouse gases. We can measure it in the laboratory. You know, the apparatus, as you see in this picture, is always a little more complicated than just the principle. But the principle is basically you put a gas like water vapor or carbon dioxide or methane in a glass tube, shine visible light at it, shine infrared light at it, and see what happens. And you measure how the infrared light is affected by this gas. The reason it's this weird old picture is because these measurements were first made in 1859. This is not new science. The greenhouse effect has been measured for more than 150 years. And in fact, I learned relatively recently that 1859 wasn't even the first. It's the one we hear about from John Tyndall, but turns out it was first done in 1856 by a woman named Eunice Newton Foote, and she deserves a lot more credit than she's gotten. Apparently Tyndall did credit her, I believe, but that got forgotten over time. And so we measure in the laboratory how these greenhouse gases affect the energy from the sun and the infrared light being returned. And once you've done those measurements, you can then calculate, based on how much greenhouse gas there is in an atmosphere, how hot would you expect a planet to be. The only possible problem we would have at this point is you always wonder, okay, we measured it in the lab. Could there be something else going on in the real world that would make it more complicated than just these measurements from the lab so it doesn't actually turn out the way we're predicting? Well, there's a good way to test that. Test it with real worlds. And so we do. We can calculate the temperature that we would expect if the greenhouse effect really does work the way we measured it in the laboratory, or if it doesn't exist. And then you compare the predicted temperature of a planet to the actual temperature of a planet. And what we find in every single case for all the planets and moons with atmospheres, when you include the greenhouse effect, you get the right answers. When you don't, you do not get the right answers. So that's confirmation that the way it works in the laboratory is the way it works in real worlds. And one of the things that's really interesting about that is, for example, here is actually a page out of my children's book on global warming, and you can see that's the actual equation for calculating the temperature of a planet without the greenhouse effect. It's a little more complicated with the greenhouse effect, but without it, that's the calculation for Earth. That's a negative sign right there. So it's showing you that if there was no greenhouse effect, just based on our distance from the sun and our cloud cover, the expected temperature of the Earth would be negative 16 degrees Celsius for the global average temperature. That's way below freezing, which means without the greenhouse effect, we would not have life on Earth, at least not the kind of life we have now. It would be too cold. This planet would be frozen. And that brings us back to our tale of two planets. The reason we're this warm instead of way below freezing is because we have enough carbon dioxide in our atmosphere to make our planet livable. So the greenhouse effect, sometimes people tell you the greenhouse effect is a problem. It's not. The greenhouse effect is the reason we're here. It's a very good thing for life on Earth. The difference on Venus is that Venus has about 200,000 times as much carbon dioxide in its atmosphere as Earth does. And that gives it a much, much stronger greenhouse effect. So instead of only warming it up to 15 Celsius, it warms it up hot enough to melt lead. So the way I like to think about this is our planet shows us that the greenhouse effect is a very, very good thing for life. Venus is kind of proof that it's possible to have too much of a good thing. And we're really almost done with the science of global warming already. Because I've shown you, we understand exactly why planets are as warm as they are. We understand that more greenhouse gas means higher temperatures. And we know that we are increasing the amount of greenhouse gas in Earth's atmosphere. How do we know that? Because we've been measuring it. This graph shows you the measurements that were begun in the late 1950s on Mauna Loa in Hawaii, of the carbon dioxide concentration in Earth's atmosphere. It's sometimes called the Keeling curve because the scientist who was making the measurements initially, Charles David Keeling. And you'll see what he measured was that in 1958 here, the greenhouse gas concentration was about 315 of these units called parts per million. What does parts per million mean? It just means that out of every 1 million molecules of air, 315 of those molecules were carbon dioxide. That's not much. That's much less than 1%. But it's important because carbon dioxide is a greenhouse gas that absorbs infrared light. Most of the atmosphere is nitrogen and oxygen, which have no effect on infrared light and therefore don't warm the planet at all. And you notice it's gone from 315 or so parts per million in the late 1950s up to over 400 parts per million today. Now, one of the questions you might ask is, why? The answer is because we've been burning fossil fuels. You might then ask, how do you know? And that was one of the great things about writing the book is early on when I did these talks, I spent 5 or 10 minutes giving you the 4 lines of evidence that show that this is our carbon dioxide that we're adding in the atmosphere. Now I'll tell you, just go look online if you want to see the evidence because we have too much to cover to spend that time on it. But there is no doubt that this is our carbon dioxide being added to the atmosphere. So we see that we're increasing the concentration of this gas that we know warms planets. And really the only question you might still have at this point is, okay, we see that we're doing this, and we've been doing it at least since the 1950s when it was being measured. But could it be that this kind of thing happens naturally on its own sometimes anyway? In order to do that, you would want to know what was the carbon dioxide concentration like in the past before people were measuring it. And you might think, gosh, that's going to be a problem because nobody was measuring it. But it turns out there's a bunch of different ways we can measure the carbon dioxide concentration in the past, even though we weren't doing it in the past. And the most reliable records actually come from these things called ice cores, where the scientists drill down into the Antarctic ice and they bring up these big tubes of ice. Well, what are they doing? So you're drilling down in the ice and you're bringing up this tube of ice that goes down. What is the ice in Antarctica? Well, the ice in Antarctica is snow that fell in the past and piled up year after year after year. And it turns out, because of the variations that happen around the Earth, that you can actually, much like tree rings, you can count the layers in these ice cores and count back how many years you're looking into the past. And there's air bubbles trapped in these ice cores. And so, again, it's always harder in practice, but the principle is simple. You count down 50 layers, and that's 50 years ago. Find an air bubble in it and measure its carbon dioxide concentration. And thereby you can put together a record of the past from your ice core. Now I'll blow your minds. The deepest ice core that's been drilled, they went down 2 miles into the Antarctic ice. And at the bottom of those 2 miles, counting back the layers, they're looking at snow that fell 800,000 years ago. And therefore, we have an 800,000-year record of the carbon dioxide concentration on Earth. And I'm going to show it to you. There it is. Here's the present, 100,000 years ago, 200, 300, and back to 800,000 years ago from the ice core data. Here's the carbon dioxide concentration. And what do you notice? Sure enough, it does vary naturally. We didn't have anything to do with all these changes. We weren't burning fossil fuels back then. It does vary naturally. But in all that period, it varied between about 180 parts per million at the bottom and about 280 at the top. And in fact, in the year 1750, kind of when we typically mark the beginning of the Industrial Revolution, when fossil fuels were starting to be burnt more, it was about 280 parts per million. Now, it's shot up to over 400. What does that mean? It means that today's concentration of carbon dioxide is about 40% higher than it ever was in the past 800,000 years. And if you take this curve and you extrapolate upward, you assume we keep doing what we've been doing, you'll find that it's going to reach 560 parts per million, which is double what it was in 715, only about 50 or 60 years from now. So if you're a college student today, this is well within your lifetime. You won't even be old yet. And it'll reach triple that value, nearly 1,000 parts per million, by the middle of the next century, if we keep going like that. 1,000 parts per million is a level that hasn't been seen on Earth since the time of the dinosaurs. You now understand all the science of global warming. So to summarize it, I like to call it a global warming 1, 2, 3. So just think about what we've talked about and let's put it all together. Number 1, it is a fact that carbon dioxide is a greenhouse gas that makes Earth warmer than it would be otherwise. There is no scientific dispute about this fact. When you hear about debates in the media, this is not something they're debating. All scientists understand and agree that the greenhouse effect makes planets warmer than it would be otherwise. Number 2, it is a fact that the use of fossil fuels is adding carbon dioxide to the atmosphere. I showed you the data that show that we are in fact increasing the carbon dioxide concentration in Earth's atmosphere. Again, that's not disputed either. Everybody can see those measurements. No one disputes that the concentration is rising. So now think about it. Number 1, more greenhouse gas means warmer temperatures. Number 2, we're putting more greenhouse gas in. Number 3 is then kind of obvious. It's going to get warmer. we expect global warming to be happening. This is the basic 1, 2, 3 science of global warming. It's obvious that we're going to have global warming given what we know and what is happening. Now we come to the hard part. If it's so obvious, why do politicians have so much trouble understanding it? So here's your quiz question. Who was the first major global leader to go, oh, 1, 2, 3, yes, global warming's a big problem, and we're causing it?
Margaret Thatcher.
Good. Somebody studied in advance. Most people guess Al Gore, right? Most people guess Al Gore. And I will say, in Al Gore's favor, he may well have understood this before Margaret Thatcher did. But in 1989, he was a senator from Tennessee. Outside of Tennessee, very few people had heard of him yet. Here's what Margaret Thatcher said to the United Nations in front of an international office in 1989. What we are now doing to the world by adding greenhouse gases to the air at an unprecedented rate is new in the experience of the Earth. It is mankind and his activities which are changing the environment of our planet in damaging and dangerous ways. You'll notice she gets the 1, 2, 3 science. There's no equivocation here. It's not maybe this is a problem, maybe it's not, maybe it's our fault, maybe it's not. No, it is a problem, it's our fault, and it's dangerous and damaging. And you remember, Margaret Thatcher is generally considered to be one of the 2 founding icons of modern conservatism, along with Ronald Reagan. So if anybody ever tries to tell you that global warming is somehow a liberal issue, just remind them that the first major global leader to say, no, this is real and dangerous, was the founder of modern conservatism. It's not a political issue. And it's even more impressive, you can see she said that in 1989, because in 1989, well, the 1, 2, 3 science is very simple. Of course she understood it, but at that point, the data weren't all that clear yet, because you'll see here, this is a graph that shows you Earth's global average temperature from 1880, when we have records beginning, up till the present. The 0 line is the 20th century average. And you can see the fact that it's warming up is pretty obvious right away, right? But if you look at 1989, if you cut it off right here, at that point you might have been able to say, you know, it still looks random. So she was sure, even though the data hadn't yet caught up to what we knew the science was. Today, the data has clearly caught up. So why is there still a debate about a topic like this? What is the debate? If you look carefully at the debate that you hear in the news, and now that you understand this 1, 2, 3 science, I think you'll be able to see this. No one ever debates the 1, 2, 3 science because everyone agrees with that. The debate is always over some detail. Mainly, in simple terms, the debate is not over whether it will warm. Everyone agrees it will. The question is how much, how fast, and how bad will it be for us? But notice the difference when you say, are we debating whether global warming is real? We're not. When you say we're only debating how bad it's going to be. Changes the nature of what you're hearing in the news when you think about it. In the book, I go through 4 major common skeptic debates that you will hear. None of them are dumb. The skeptics are not dumb people. They're scientists, they're smart people. They raise interesting points. I don't think they're correct. Most climate scientists don't think they're correct, but you do have to think carefully through what they're saying and come up with the answers to them. And in the book, I go through that and for the 4 major debates. But here, since I want to move quickly through to get to our solutions, I'm just going to focus on a couple of the most common ones that you will hear. So for example, one of the most common points you'll hear is that, okay, well, yes, we do expect it to warm up, and yes, it is warming up, but maybe this warming is still not the part due to us. Maybe this is due to something else, some natural factor. Well, then you have to ask, well, what natural factor could it be? And it turns out, when you go through this in some depth, the only natural factor that could possibly be accounting for this would be changes in the sun. And you've probably heard some people say, yes, it's the sun. But we can look at the data, and here's the data. So these two graphs, this blue curve shows you the amount of energy reaching Earth from the sun, and it does vary a bit. The variations are very, very small. You'll see these are much less than 1% on this scale. And this is the same data I showed you for the temperature before, except for instead of a bar chart, it's smoothed out in a graph. For those of you who know a little bit more, both of these curves are smoothed over an 11-year average to match the sunspot cycle. And what you'll see is that from 1880 to about maybe 1950 or so, the sun was getting a bit brighter, and the temperature was going a bit up, and you could kind of believe that that was the cause of that. But since that time, the sun's actually gone down, and the temperature has gone back up, kept going up. That means it's not the sun. That just rules it out completely. And in fact, there's a whole bunch of other ways we can rule out the sun. For example, if it were the sun, the entire atmosphere of Earth would be warming up. In fact, if it's the greenhouse effect, the greenhouse effect predictions say it warms up in the lower atmosphere down by the ground, but cools in the upper atmosphere. And guess what? The measurements show it's cooling in the upper atmosphere, exactly as predicted by the greenhouse effect. It's warming more at night and more in the winter than in the summer. Those are both things explained by the greenhouse effect, but not if it were the sun. So it's not the sun. Another very common argument you'll hear from the skeptics, maybe the most common one you hear these days, very few of them bring up the sun anymore since this data is so easy to show and rules it out. The most common argument you probably hear today is that, okay, well, yes, it is warming up, the climate is changing, but the climate has always changed. So who cares, right? Changes happen, and sometimes naturally, sometimes due to us. What difference does it make when you have a change in climate? So to look at that, I want to go back to our ice core data. And you'll notice the same graph that I showed you before, going back 800,000 years, but this time I've put on a second graph. And this graph is the global average temperature going through those 800,000 years. It's a little more difficult to measure. You have to look at isotope ratios in the air bubbles and so on, so it's a little more complex. But basically you see, low is cooler, high is warmer. And notice that these are degrees Celsius here. So these are very large swings in temperature, 8 degrees below the average to 6 degrees Celsius above. So for Fahrenheit, you would effectively double that. These are very, very big swings in temperature that have occurred on Earth. And that won't surprise you because all these bottoms here are ice ages where glaciers come down over much of North America and Europe. And the peaks are the interglacials when the glaciers retreat. What do you notice when you look at the two graphs together? You notice that whenever it's warm, the carbon dioxide concentration is high. And whenever it's cold, the carbon dioxide concentration is low. And that's what we expect because of the 1, 2, 3 science. They go together. This is further proof that what I've told you about the 1, 2, 3 science is correct. And so you can look at this and say, well, yeah, the temperature does change naturally, so why should we be concerned right now? And the answer is, there's a couple answers. One is, notice that we're already in an interglacial period up here at a high temperature before we even started shooting the carbon dioxide concentration way up. Secondly, even though we're still in a range that has been seen on Earth over the past 800,000 years for temperature, we're in a range for carbon dioxide that goes way beyond that. So that might suggest, hey, there's at least some risk that this is going to keep pushing up to much more dangerous levels. And again, I don't have time to go into detail here, but you'll find most of the debate that you hear today from the very few scientists who dispute how bad global warming is going to be is over what they call the climate sensitivity, which is if you double the carbon dioxide concentration, how much more will that go up? Most scientists think it'll go up significantly. A few say, there's probably some feedbacks in the atmosphere that'll make it not go up all that much. We can't be sure that they're wrong, but among scientists who've looked at that, roughly 97% think that it's likely to go up significantly and that therefore we have a serious problem on our hands. What is this serious problem? If the temperature warms up, Why does it matter to us? The answer is because of the consequences. So I told you the science, the consequences, the solutions. Now we're on to the consequences. And there are 5 basic consequences that are predicted for global warming. And in fact, you'll see we're already experiencing all 5 of them. The first one is that even though I've been speaking about global average temperature, we don't expect the whole Earth to warm by the same amount. Some parts are going to warm by more than others. So we get what we call regional climate change. And in fact, this is why a lot of scientists prefer the term climate change to global warming. Personally, I like global warming as a term, but either one is fine. To show you regional climate change, I have this map here. This is made by NASA, and what they've done is they've compared to the 20th century average, which is the right in the middle. Blue is cooler, red is warmer, and you'll notice right here it says 1880 to 1884. It's all 5-year smooth data. So it shows you around the world how temperatures were compared to the 20th century average. And they've made a movie to show you, and so you notice the years running by here, right? And as you watch these decades go by, you'll notice, temperatures change around the world, right? Climate change is natural. And in fact, it goes up, it goes down, and there's not really an obvious pattern as you watch those first few decades go by. Just keep watching. Keep an eye on the years, too. I think the pattern became clear, didn't it? And you'll notice warming much more in the Arctic than in other parts of the world, which we'll come back to in a moment. Another example of regional climate change has many effects. This is just showing you temperatures. Here's another way of looking at these temperature changes that this graph's actually not in the book because it came out after I wrote the book. This is from James Hansen, very well-known climate scientist. And what he's done here is he's basically taken all land areas in the northern hemisphere and normalized their summer temperatures from 1951 to 1980. So it's the number of days with a particular temperature. So most days are, by definition, normal. But of course you get a bell curve, just like you do for any kind of data set like this. Some days are cooler, some days are hotter, and a very few are extremely cold or extremely hot. And this is the graph he made for the whole northern hemisphere for the period 1951 to 1980. That's the graph for the last 10 years. Notice, compare them. It has moved, if you know statistics, it has moved a full standard deviation to the right. What we used to call, what we now call normal, right, the most common days, is what we used to call hot. What used to be extremely hot is now fairly common. Okay, and you've noticed this. We have a lot more hotter days. And I know around here, you're particularly attuned to some of the things that happen as a result of that. And incidentally, in terms of this regional climate change, it's worth just pointing out because one of the things you'll hear sometimes people say is, wait, you told us that the dryness and drought was caused by global warming, and then you tell us that the floods are caused by global warming. Which is it? And the answer is, it's both. And it makes perfect sense when you think about it. What happens as you warm the earth? You have more evaporation. If you're in an area that happens to be dry at a particular time or in general, more evaporation is going to make it even drier. But you also have more total moisture in the atmosphere, which means if you're in an area where it's going to rain, there's going to be more rain to fall. So a prediction of global warming is that when it rains, it pours. And guess what? The data show that happening too. In fact, more generally, we expect to get an increase in storms and extreme weather. And this, again, is really easy to understand. Remember, what is global warming doing? It's trapping heat down in Earth's lower atmosphere and on the surface, land and oceans. What causes weather? Heat and energy. Hurricanes are driven by heat from the ocean. So as we increase temperatures, you expect more extreme weather events. Hurricane Florence, which is aimed at the East Coast right now, has strengthened dramatically as predicted. How did they know it was going to strengthen dramatically? Because the water temperature is 3 degrees higher than normal or what used to be normal. And that's going to drive it to more extremes than it would have been driven otherwise. A third major consequence, remember I told you about, I showed you the graph showing, the map showing that it's been warming more in the Arctic. Well, that melts sea ice. And so we're seeing a big decline in summer ice coverage. Shows you 3 particular years there, and the graph for all years trending downward. Less ice in the Arctic Ocean in summer and in winter than there used to be. That actually turns out to be particularly scary because ice reflects sunlight. And remember, the amount of energy that Earth absorbs depends on how much of that sunlight is reflected into space. As we melt the ice, we absorb more sunlight, and that actually amplifies global warming even aside from what we're doing with adding more carbon dioxide to the atmosphere. The fourth major consequence of global warming is a rise in sea level. And the rise in sea level happens for a couple of different reasons. It actually has nothing to do with the melting of Arctic ice, because that ice is already floating. It has to do with thermal expansion of seawater as it warms up, and the melting of landlocked ice, so ice from glaciers, particularly in Greenland and Antarctica. And we've, as a result of that, already seen a 1-foot rise in sea level over the past century due to thermal expansion. And thermal expansion will make sea level rise another foot by the end of this century. And a foot might not seem like that much, but when you have a storm surge, like here's Hurricane Sandy, it gets amplified. And that has a lot of consequences. But you then have also, in addition to that foot from thermal expansion, whatever the melting of ice into the oceans does. Unfortunately, scientists don't have a really good grip yet on how fast we expect the ice to be melting into the oceans. We can measure what's happening right now thanks to these satellites called GRACE, which the first round of them died last year, but the replacements were launched earlier this year. They can actually measure the amount of ice over Antarctica, Greenland, and so on. So we can measure how much the ice is declining, but we're not very good at predicting how much it will continue to decline in the future. So there's a lot of uncertainty about sea level rise. Most scientists guess, and I say guess because we don't really know, that we're going to get about 1 meter of sea level rise by the end of this century. That's going to be pretty significant in San Francisco, for example, right? Or here in the eastern seaboard, the red areas that would be flooded by a 1 meter rise in sea level. But if you want to think about what the possible range is, it could be less than 1 meter, but at the extreme, some scientists have estimated we could get as much as a 6 meter rise in sea level. That's 20 feet. That's more than the ceiling here. Think about the impact of that along the California coast. And I think it's worth, one of my goals here is not to scare you, because these are serious problems, but we can solve them. So don't get scared by this, but it is worth thinking about what would happen if we kept going with what we're doing and melted all the ice. That's not unlikely. In fact, if we keep doing what we're doing, we will end up melting all the ice in Antarctica and Greenland. The Earth, back in dinosaur times, for example, was ice-free, didn't have polar caps. The good news is, even in the worst case scenarios, it'll take us a couple thousand years to do that. So in principle, as that ice melts, people can migrate inland. The part that I want you to think about is that if we did that, sea level would rise by more than 200 feet, which means that our descendants a couple thousand years from now will need deep sea diving equipment to visit the ruins of today's coastal cities. I think that's an image worth thinking about and keeping in mind when you're considering what might happen. And the fifth consequence of global warming, the fifth major consequence, is one that you don't hear much about, but is actually very, very important, called ocean acidification. As we add carbon dioxide to the atmosphere, it's not all staying in the atmosphere. A lot of it is being absorbed by the oceans. And when it gets absorbed by the oceans, it turns into carbonic acid that makes the ocean water more acidic. So that's why we call it ocean acidification. That's been implicated in some of the coral bleaching that we've seen around the world, declines in global fisheries and so on. And in fact, there's a lot of scientists, political scientists, who think that ocean acidification could actually cause more human impact than all the others put together because of the fact that so many people around the world depend on the oceans for their food supply. It's also worth noting that you may hear about geoengineering techniques, ideas for combating global warming, such as seeding the atmosphere with particles that reflect sunlight, or even putting giant mirrors out in space to reflect sunlight, so that as the Earth warms, we reflect more sunlight and don't cool it down. Well, the thing about that is, in principle, first of all, those I think are risky technologies because we don't know what other side effects they might have. But even if they worked, they would only work for those first four. Because as long as you're still putting carbon dioxide in the atmosphere, you haven't done anything about ocean acidification. Which means, as far as I'm concerned, all those possible geoengineering schemes that involve reflecting more sunlight are fatally flawed because they don't solve one of the major problems, maybe the biggest human impact problem. The only geoengineering, in my opinion, that could possibly work is geoengineering in which we actually remove carbon dioxide from the atmosphere. People are working on that possibility, but we don't know how to do it yet, certainly not at the scale that would be required to undo what we're doing today. Those are the consequences. I told you I would talk about solutions, so I'm going to move into that. This is the part where I try to give you more hope after scaring you, right? So why do I say that this is a solvable problem? Because basically, you know, the key to solving any problem is to understand it. Once you understand the problem, then you can figure out what the solution to the problem is. Works for math, physics, chemistry, English, anything, right? We understand this problem. 1, 2, 3. The problem is being caused by our release of greenhouse gases into the atmosphere. Given that we understand that that is the cause of the problem, the solution to the problem is actually very, very simple. Stop doing that. Of course, the reason we're doing it is because we're getting our energy from it, and we like energy. So if you just tell people stop doing it, well, that's not going to work. You need to have something to get your energy from that doesn't involve the things that are causing the problems, the fossil fuels and the release of the carbon dioxide. But it turns out we know how to do that. We have existing technology right now so that if we decided we wanted to stop using fossil fuels but have no decrease in the amount of energy available to us, we could do it through a combination of these three technologies. Energy efficiency, right? If you use more efficient devices, then you don't need as much energy in the first place to get the same benefits. Number 2, renewables, for example, solar power. 20,000 times as much energy as we use as a civilization is hitting the Earth from the sun, so we'd only have to tap 1/20,000th of it to go completely solar. What's similar for wind, it's about 15 times, so we could do it with wind. And then nuclear, a lot of people have different opinions about nuclear technology, but one thing nuclear technology does not do is release greenhouse gases. So nuclear is a solution to global warming, whether or not you think it's a solution to other things or the solution you would want. And it could be that, well, this one by itself can't solve the problem, but efficiency could probably solve about 1/2 to 2/3 of the problem, maybe even more. And the rest we could probably solve with renewables alone, or with nuclear alone, or with some combination of them. The point is, if we really cared, we could do it right now. And we have all these future technologies that will be able to do even more. Algae-based biofuels, one of my favorites, solar energy from space where it's never dark and never cloudy, nuclear fusion, which we have not figured out how to do yet, but if we could, the water flowing from a single kitchen faucet, if you could extract the hydrogen from it and fuse it, could power the entire United States. So you can see these incredible technologies on the horizon. So the question then becomes, if we already could do it, and we have technologies on the horizon that could do even more, what's stopping us? And the answer has been very simple. It's been cost, right? Fossil fuels have been cheaper to get our energy than any of those other things have been. Now that's already starting to change in the market, but it's worth thinking about that because when you say cheaper, that assumes you have accounted for the actual cost. But economists will tell you that there's a bunch of costs of fossil fuels that we have not accounted for when we price them. They're what the economists usually call externalities. I like to think of them as socialized costs because they're costs that instead of paying as the user, you force everyone in society to pay for you. For example, according to the NIH, air and water pollution cost us at least $120 billion a year in hospitalizations due to that effects of that pollution. That's hospitalizations. That's not just I didn't feel good and I didn't work as efficiently. That's actual hospitalization costs. And notice, that is not like not a real, sometimes people say, how much value would you put on the trees? Okay, I mean, that's nice, but that's not real money. This is real money. You're paying that $120 billion for that air and water pollution. It's just you're not paying it when you buy gasoline or coal power. You're paying it through your insurance premiums and your tax dollars. The Department of Defense says we spend at least $100 billion a year on our baseline cost for maintaining our fleet that protects the global fossil fuel supply. Again, that doesn't include the wars in Iraq, Afghanistan, and so on. That's just the baseline cost. That's real money. You're paying for that with your tax dollars. Then there's direct subsidies that we give to oil and fossil fuel companies for tax write-offs, production subsidies, and so on. Those add up to about 20 billion plus a year. They're actually small compared to those first two numbers. But the key point here is these three costs, nobody disputes these. These are real costs that you're actually paying. And the amazing thing is if you put them together, they add up to about $300 billion a year, roughly. And if you look it up, you'll find we use about 150 billion gallons of gasoline a year in this country, all of us together, which means that these three costs alone represent a $2 per gallon subsidy for your gasoline. Socialized costs, right? You don't pay for it when you buy it. We make everybody in society pay it as a whole. And that's only the beginning, right? Then you can say, well, all the terrorism and totalitarianism that we're facing around the world, think about it. Iran, ISIS, Al-Qaeda, Russia, all the sort of bad actors around the world, where do they get their money from? Almost entirely from we've given it to them buying their fossil fuels. So those costs have been fueled by what we have been handing over to them. If we weren't using fossil fuels, they would not have revenue, at least not as much. And then there's the environmental damage and so on. In fact, the IMF did a study a few years ago and found that global subsidies for fossil fuels, without even considering future damages from global warming, are $4 trillion per year. So we're actually spending as a globe $4 trillion more per year on fossil fuels than we notice when we go and buy it. If you divided that over the cost of them, it would amount to many, many dollars per gallon equivalent. If that was part of the price, no one would buy fossil fuels. And that's why for economists, whether they're conservative or liberal, they all basically agree that the solution to this problem is to build that into the price in some way, most commonly through a carbon tax. And again, to get back to the idea that this is not a political topic, you'll see that this was a report written by all former administration officials for Republican presidents, and they call it the conservative answer to climate change. And what's their answer? It's to add a carbon tax with a catch, right? They're conservatives. They don't want the government to have any more money. So you have a carbon tax, but the government gives it back immediately. Every month, the government mails out dividend checks to every American in equal amounts for all the money they took in through the carbon tax. How does that work? It works because it means the more fossil fuels you use, the more you spend on the tax, but you're getting the same check no matter what. So it's in your favor to use less so that you've got that net positive. And what's really amazing is what they said about it in their paper here. They said how this new climate strategy, this carbon tax and dividend plan, can strengthen our economy, reduce regulation, help working class Americans, shrink government, and promote national security. And it's worth parsing that for a moment to see how you get all these effects from this one solution that they propose. How does it strengthen our economy? Because we're actually overpaying for our energy right now. When you include those socialized costs, every other energy source we could use would be cheaper. So if we did this, we would switch to sources that would be giving us the same or more energy for less money. That strengthens the whole economy. How does it reduce regulation? Because why did Obama put on the Clean Power Plan and so on? Because we don't have a carbon tax, so you try to regulate it in some other way. But if you had the carbon tax, they would argue, we don't need any regulations on it because the market will take care of it. How does it help working class Americans? Those dividend checks. On average, less affluent people use less energy, and therefore they're going to have a net gain from the dividend checks. How does it shrink government? Well, that's back to the reducing regulation. And how does it promote national security? Because we're not sending money to terrorists anymore. In fact, when you put it all together, you get my favorite cartoon here from Joel Pett down in Kentucky. And you can see the guy talking about all the benefits we get if we switched our economy from our current fossil fuel to economy to the other. And the person in the audience asking, well, what if it's all a great big hoax and we create a better world for nothing? You don't even have to believe in it and everything I've told you to still see that this is better. So to close, I want to have you think about it. Hopefully I've given you some insights into the basic science and what the debate is and is not and what we can do about it. But how do you get people to really internalize it and say, I'm going to do something about it? And the way I like to think about it is with what I call a letter to your grandchildren. So imagine writing a letter to your grandchildren and sealing it in a time capsule to be opened 50 years from now. Why did I pick 50 years from now? Because on average, in 50 years, your grandchildren will be the age you are today. Now, I know your college students don't have grandchildren, but in 50 years, on average, you will, and on average, they'll be in college just like you are right now. And if you're retired today, your grandchildren, on average, in 50 years, will be retired just like you are. So it's like writing to your future self, but it's to your grandchildren. Dear grandchildren, as I write this in 2018, many people are arguing about whether global warming is real, and if so, how serious it will be for you when you were my age. I have examined the evidence, and I have decided to, and then you fill in your decision. Hope your world is a good one. Love. You seal it in the time capsule and ask yourself, what are they going to say about what you did or did not do today when they open that 50 years from now? And I think if everybody does that, we can get away from all the political disputes and come to an agreement that works for everyone in the United States that will solve this problem and solve it not just for us, but for the whole world. So I'm basically going to stop there. Again, you can find the book online at globalwarmingprimer.com. You can also order a copy from there. And I have a children's book, The Wizard Who Saved the World, that covers the same material but for kids. And I just want to tell you about one thing that's kind of cool about this that I'm excited about. You'll notice it's in space. And that's because of this really cool program called Storytime from Space. I just want to show you a brief clip from a different book here. Hopefully this will play. Oh, it's not playing.
Audio's ready. I got it.
Hi, I'm NASA astronaut Mike Hopkins on board the International Space Station, and it's one of my favorite times. It's story time from space. Now today's story is Max Goes to the Moon, a science adventure with Max the dog.
So that's another book I wrote that is not about global warming, but was read for this program also. So go to storytimefromspace.com. You'll see videos of astronauts reading books to kids. It's a really cool program. I hope you'll check it out. I want to just tell you one other thing I hope you'll check out, in fact, do right now if you can, is download this app that we created called Totality for learning about solar eclipses, but it does also have a section on global warming in the app. It's free, so you can go to the App Store right now and download it. And those are my books. Those are the kids' books that are up in space. There's Global Warming Primer, some of my others in my textbooks. And if you're interested in buying any of them, there's a 30% buy direct discount, which makes like this one and all of those $10.50 each if you go to my website, bigkidscience.com. And that's where I stop. Thank you.
Of 15 minutes to ask questions, but I know some students have this conflict at 5 that they need to get off to classes or to work. I'm going to ask people to quickly and quietly leave the room in the next 90 seconds. So get your materials and head out these doors, and then we will continue with a question section for the rest of us. If anyone needs to sign this, please take it outside. You can sign in for those of you who are attending for extra credit. This is just a little easier, and we get the.
Yep.
Anyone need this? Do you mind taking it outside? There's a small table there, and leave it there. Thank you. Okay, we're going to be able to move on to the questions here very shortly, and I know there's going to be a lot of interest in this.
Oh, thank you very much.
Let's start with the first question for Dr. Bennett. Yes, Phil.
Yes. Molecule for molecule, isn't the water molecule a better greenhouse absorber than a CO molecule? And then in a sample of air, we imagine that there are more water molecules than there are CO2 molecules. You've only talked about CO2. Can you also address?
Yes. So I'm not sure the answer to the molecule for molecule, but I do know overall, water vapor contributes 10 times as much to the greenhouse effect on Earth as carbon dioxide.
So some people would say, why worry about CO2 then?
Right. And the answer is because water vapor is just going along for the ride. Carbon dioxide is the controller. And the reason is because water vapor is so rapidly exchanged between the ground, the oceans, and the air. So it responds to the temperature. You warm it up a little bit, more water vapor goes up. You cool it down a little bit, more water vapor goes down. So carbon dioxide is the driver. An analogy I like to think of as a bicycle, right? Water vapor is the wheel that's making you move fast down the road. Carbon dioxide is the crank that's driving it. And that's basically the answer to that question.
Yeah, you're welcome to pick your own question. We'll go with James here.
So on your graph comparing the solar output to the temperature on Earth, your units for the solar axis were in irradiance.
Mm-hmm.
I was expecting it to be like a temperature output from the sun. Can you explain why it was irradiance?
Because irradiance is the measure of what's happening at the top of Earth's atmosphere. And so the temperature of the sun's not really varying. It has more to do with the sunspot coverage. That's why it is affected by the sunspot cycle. So when there's more sunspots, less irradiance in general coming toward Earth. So that's something that we can measure pretty well and document pretty well.
Yeah, a quick clarification. My recollection on this, and this is this issue, is the sunspots, that there's more brightening in the what's called the faculae interstitial during periods of major solar activity. So I think
there's the I may be wrong in this, but my memory, because it's been a long time, my memory is that the visible irradiance drops with the sunspots, but the UV and X-ray
increases.
up.
That's the sort of, I love this because that's the sort of thing that scientists think about in terms of the drivers in the solar cycle of how much irradiance or energy per time per unit area is hitting the upper portion of the.
And the other reason that that's a good unit to use is because nobody's asked, maybe somebody was going to, but why do we have those big natural cycles with the ice ages and so on? And the leading theory behind that is what's called Milankovitch cycles, which is small changes in Earth's axis, tilt, and orbit. So that the sun's not changing, it's the irradiance changing because of the way we're. Yeah.
Very good. Jim.
Well, I wanted to say how much I enjoyed your presentation. You clearly spent a lot of energy in organizing this whole thing. I attended a talk a short time ago, and the fellow made several points, but two of which I'd like to present to you and just ask for your comments. And one was that The issue of climate change is what he called a wicked problem, which I guess is a technical term amongst political scientists, which
I don't know it, but
well, which diminishes the effectiveness of arguing from the point of view of science. He said you, those who believe in science, you should reframe your position in terms of values in order to better communicate with those who don't believe in science. The second point that he made that I'd like to have you comment on was that if there's stalemate at the national level, real change is going to come at the local level. And that, so individual communities will start getting into conservation or have regulations on, burning wood. And we can't, in Santa Rosa anymore, you can't have a fire. And, we've all got, homes with fireplaces in them and you can't put a fire in it, sort of thing. So that you'll find regulation that addresses the issue at the local level, but you probably are going to have trouble at the national level.
well, so let me go back to the first question. Yeah, there's been a lot of research going on in terms of what do people respond to, and values is important. But I do think, part of what you see here is it's hard for me to attract an audience of people who are maybe not going to believe in this to begin with. They might not come. But there's a scientist named Catherine Hayhoe, fantastic climate scientist, who also happens to be an evangelical Christian. And she's had great luck with the evangelical community in communicating this, because she comes in being able to say to them, I hold the same values as you do, so it gets them to listen. But once they're listening to her, I think that they listen to the science, because nobody wants to say, I don't believe in science, right? It's just getting them to listen in the first place where I think those things come in particular into it. How do you get people to say, okay, I'm willing to open my mind and think through this in a critical way? As far as the driving, a couple things on that. First, obviously I'm in favor of local initiatives, individual initiatives, and so on. But global warming is a global problem and it requires a global solution. For example, even the United States, historically, we've contributed by far the most to global warming, but today we're not a big contributor anymore compared to China and India. And so what we need is a solution that brings the whole world along. And one of the reasons I like the carbon tax is, maybe I'm naive, but I happen to be a big free market proponent. And I believe that innovation happens through the free market. I think if we put on the carbon tax, we'll find pretty quickly that not only has that made all these alternatives cheaper than fossil fuels, but the innovation will happen so rapidly that pretty soon they'll be cheaper than the fossil fuels were even without the carbon tax. And as soon as that happens, the rest of the world will say, gosh, why am I spending more on fossil fuels when I can have cleaner energy for less? And they'll buy it from us. So to me, the only question, and I actually think this problem is going to be solved because the technology's there, it'll get better. To me, the only real question is who's going to solve it? Will it be us or China and India? And this is economically, I think, the point at which our future depends. If we let them be the only ones building technology and solving it, then our economy will suffer. So I do think we have to have global solutions. As far as the national level goes, I will point out there's a group, if you haven't heard about them, you should look it up, called the Congressional Climate Lobby. And this is members of Congress who are committed to doing something about global warming, and they made a rule that in order to join this caucus, you have to bring a member of the other party along with you. And currently it has 70 members, 35 Democrats and 35 Republicans. That means, if you look at the math, that if all the Democrats and those 35 Republicans voted together, which in principle they would, we'd have a carbon tax pass. So it's possible.
You've stayed away from population control.
It's a different issue. It's clearly drives, all of environmental things are tied in with population, but it's a different issue. We already have 7.5 billion people on the planet. If we wanted to give everybody the lifestyle that they would like, which is basically the lifestyle we have in the US today, we'd be in big trouble if we did that with fossil fuels. But I believe we could do it in other ways. If that number keeps rising, then clearly that makes the problem that much more difficult to solve in the future. But it is, to me, a separate problem. I don't believe it should be ignored, but I don't think we have to do the two of them necessarily at the same time. Both need to be solved and addressed, but we can address one and we can address the other. And for whatever reasons, there seems to be different people who argue about the one than the other. So I think we can get the consensus here pretty quickly and easily. And to some extent, I'm very concerned about population, but to some extent, it does seem to be a problem that is solving itself. People around the world are choosing to slow that rate of growth. I wish it would move faster, but it is happening.
Could you talk a little bit about methane? Just the, so much more, shorter lived, but much more intense, and I just saw a thing over my phone that the Trump administration is considering releasing or opening up methane rules and allowing more methane emissions.
Right, yeah. So I have a bunch about methane in the book. The reason I don't bring it up here so much is for two reasons. Number one, methane's a fossil fuel too. So if you get rid of fossil fuels, you got rid of that problem at the same time, right? Number two, that residence time thing is very important. So methane, if we stop using fossil fuels, methane will return to its natural levels in a few decades. Whereas carbon dioxide would be tens of thousands
But it's intensifying.
of
isn't it,
years.
now?
So it is intensifying, but I'm not ignoring it. I'm just saying that when you pick your problem to talk about, the carbon dioxide is the one that presents the biggest long-term problem, and if you solve that one, you solve the methane one at the same time anyway, so,
Yep.
yeah.
We're running up on our time here. Let's get some more student questions. Zach?
I just have a relatively quick question. It seems as though if you've taken surveys of nationally, it feels as though people of between the ages of 18 and 25 seem to have a strong belief in climate change, and that belief seems to diminish as the demographic shift upward in age. Is there any plan or strategy to allow more education for those of the older demographics to understand the problem?
We're trying. Yeah, I mean, that's actually a really interesting thing, right? Because the older people have seen it happen. You're going off of education, right? Well, there's been changes in your lifetime already, but the older you get, the more changes you've seen. Why it seems that makes it harder for some people to believe in it is sort of mystifying to me. But yeah, I think the other good news part of it is polls are consistently showing that even among the most difficult groups to reach, the vast majority of them think it's real in us. I think for the U.S. as a whole, the percentage who say climate change is real and due to humans is in the upper 80s. Now, it's only among politicians that it's really been a tougher sell in a few groups. The majority of Republicans say they're more likely to vote for someone who promises action on climate change. So.
With that, we have
We have one more right here.
one
You
more,
got it?
and then but I was going to suggest that we can take questions out to the
Oh, sure.
lobby if you
We
want to
can do
continue answering questions. So why don't we do that, Shannon, if you don't mind? We'll continue with questions out in the lobby. Thank you so much. Let's give them a round of applause.